All right, guys, I am back. So I'm going to be going over a little overview of inverse functions because I'm going to introduce a new function family to my Algebra 2 students. So remember, let's look at the characteristics of inverse functions. First and foremost, when we look at two functions are inverse functions of each other if the inputs of one function, right, become the outputs of the other and vice versa. So just doing a little overview of inverse functions characteristics. So the inputs of one function become the outputs of the other and vice versa. Okay, so I'm going to remember this because we're going to look at that. Also, when graphed, these two functions reflect the line y equals x, right? So this right here is the identity function, y equals x. And then also, when composed, if I have f of g of x must equal x and g of f of x must also equal x. Okay, so both of these must be satisfied in order for this to be true. And going over the next part. So here we go. Sorry about that. Okay. Also, remember, if the inputs of one become the outputs of the other, that means the domain of one becomes the range of the other. So the domain of one becomes the range of the other and vice versa. And vice versa. Cool. Okay. So we recognize that now I'm going to be talking about the inverse function to the exponential. So now I'm going to be talking about my logarithmic function, okay? My logarithm function. Okay, my logarithm function is, oopsie, loop. I'll erase that. Again, we're live, so you know. My logarithm function there we go. Let me make that line nice and straight. There we are. This function, quick little properties of it, it's the inverse function to the exponential function. So it's the inverse function of the exponential function, okay? So this is very important. Let's look at the anatomy of the form of how we write the equation. Though the explicit equation for a logarithm looks this way. It has this like this, okay? Okay, so as we are looking at this, make sure my little tapaderita fell before I dry up my thing. Okay. So let's go ahead and look at the anatomy of this. This homie right here is my base, okay? This right here is called my logarithm, but let's also call it the exponent because this is important. I'm going to show you how this works. And this right here is called my argument. Okay, so this is the format it looks like. Whenever the relationship between the exponential function and the logarithm function is the following. So this is the relationship, okay? So far, we know that we can write the exponential function like this. Y is equal to b to the x, right? Where that's base, right? And there we go. Y is equal to b to the x. That's my base, that's my exponent, that's the function, which is f of x, okay? Now watch. what I'm going to do, I call this like my counterclockwise situation. Do you see how I say y is equal to b to the x, right? Can you see it? Y is equal to b to the x. Or we can say b to the x is equal to y. So b to the x is equal to y. See that? B to the x is equal to y. Essentially, these two things are the same thing. Yes? Awesome. So this is how it is related. These two things. Let's look at it. Here I have an output. And here, this is my input right here, right? See my input is x and my output is y, yes? So let's see if that makes sense. If I have this like this, let's see. See now here, this is my input and this is my output. Does it satisfy the definition of an inverse function that says these two are inverse functions? Why? Because the input of one becomes the output of the other, and the output of the other, so look at my finger right there, output of this one becomes the input of the other. So that's the first definition. So let's go ahead and look at a simple example. That way we can see how we can read logs. So I'm going to do some simple examples of it. Okay. Let's go ahead and see. So I'm going to go ahead and see examples of logs. That we can look at, okay? First one, let's try this one again. Where's my base? This is my base right here. I'm looking for the exponent. I don't know what the exponent is, or the logarithm. And this is my argument. So in order for me to analyze this, I like to write it in its exponential format. Again, 2 to this power equals this. So 2 to the x power gives me 8. So now I'm going to show you a quick little crash course on solving exponential functions, exponential equations. Here I have a base 2. Do I have a base 2 here? Not necessarily, but I can convert it. So remember, 8 is equal to 2 to the third. So I have 2 to the x is equal to 2 to the third, because 8 is equal to 2 to the third, so I have the freedom to go ahead and write it this way. Now that I have the same base on both sides, I am able just to take an analysis of the powers. So just by doing that, I know that x is equal to 3. So let's see if that's true. So that's going to give me my answer. 2 to the third power gives me 8. Yes, again, remember that I'm using that equivalency that log b of y is equal to x is the same thing as b to the x is equal to y. Okay, so let's see if that's true. 2 to the third power gives me 8. Is that true? It should, because 2 to the third power gives me 8. Check. So this is how I go ahead and write a logarithm. Okay? Go ahead and do another example. Okay? So let's do log 2. Let's do a different power. I'm going to do 3, and I'm going to do 81 equals x. Okay. So again, I got to look at this problem, and I'm going to go ahead and look at it in terms of its exponential format. So let's see. 3 to the x power should give me this. So 3 to the x power gives me 81. Can I write 81 as a power of 3? I sure can. Remember, 3 to the 1 is 3. 3 to the second is 9. 3 to the third is 27. 3 to the fourth equals 81. Yes? So, again, I'm going to rewrite this in terms of the equivalent base. So instead of writing 81, I'm going to write 3 to the fourth. My bases are now equivalent. So now all I have to do is analyze the powers and right there. X to the fourth 3 to the 4th power gives me 81. So all I have to say is x is equal to 4 because now log 3 of 81 is equal to 4 is true. Cool? So I need you to understand that so that now that I can prove to you that the logarithmic function is the inverse to the exponential. So I'm going to go ahead and do my lovely, beautiful parent function 2 to the x real quick. So I'm going to call p of x just because it's the parent function 2 to the x. And I'm going to go ahead and I'm going to do a couple of values, just our usuals that we've been doing. Now remember, 2 to the negative 2 is 1/4, 2 to the negative 1 is 1/2, 2 to the 0 is 1, 2, and 4. Okay? Ooh, there we go. Okay. Now remember, we said that this is the same as me saying y equals 2 to the x. So now I'm going to write the inverse function. I'm going to write the inverse function in that format. So now I have, remember, I'm going to have f of x equals log 2x. Okay, so let's see what this gives us. And remember, we were saying that the inputs of one function, since they are inverse, must be the outputs of the other. Sorry, this must be p and this will be f of x. So right here, I'm indicating that f of x is the inverse function of p, okay? Just because they're inverse of each other. Okay, let's see. We're going to go ahead and analyze this homie right here, and we'll see what we get. So let's try this one right here, my anchor point. I'm supposed to have that 1 corresponds to 0. Let's see if that's true. So let's see what we get. Is it true that if I have f of x equals log 2x, let's see. So let's see what we get. I have f of 0 is 0. Notice that my f of x is 0. 0 is equal to log 2 of x. Let's see what we get. I'm going to analyze it just like I did in my previous examples. Remember, 2 to this guy has to give me that guy. So what's 2 to the 0? 2 to the 0 is 1. So did I get x equals 1? Bam, right there. Cool, I hope I proved it to you. If not, message me. We'll do another little chit chat. Let's go ahead and now recognize then that my 2 corresponds to 1 because, again, the inputs of one become the outputs of the other and vice versa. And then 4 corresponds to 2. Let's do one more. Let's do 3 corresponds to 8 because that's my 2 to the 3rd is 8. Let's see if 8 corresponds to 3. Again, f of x equals log 2x. I know that my f of x is 3. So 3 is equal to log 2 and 8. Let's see if that's true. Okay, watch. 2 to what power gives me that? 2 to the 3rd equals 8. Is that right? Yes, it is. So I hope you recognize that. And now for the sake of just simplicity, we're going to say that 1/2 corresponds to -1 and 1/4 corresponds to -2. So far, my first characteristic of inverse function has been satisfied, indicating that the inputs of one function become the outputs of the other and vice versa. So we're looking at, this is now my new function that I'm looking at. Again, base 2, they must match. And let's go ahead and graph and see what we get. So I'm going to go ahead and graph this. And so -4, 4, -4. Okay. Okay. So I'm going to go ahead and graph my p of x, which is my parent exponential function in blue. Again, 0 corresponds to 1, 2, 1 corresponds to 2, 2 corresponds to 4, 3 corresponds to 8, negative 1 corresponds to 1/2. So here is my parent function. This is 2 to the x. And now I'm going to go ahead and graph my f of x function, which is now the logarithm. I have my table of values here, so I can just go ahead and do that. So let's see, I have 1 corresponds to 0, 2 corresponds to 1, 4 corresponds to 2, 1/4 corresponds to negative 2. So now I have something that goes like this. And welcome now to this homie right here is your logarithm function. Now let's go see and make sure that it satisfies my definition that when two functions are inverse of each other, they reflect across the line y equals x. Do they? Yes, they do. So let's talk about some properties of the logarithm function. Remember I said the inputs of one become the outputs of the other? This homie right here has a domain and range of negative infinity to infinity. Oh, that's my range. I mean, my domain. My range is non-inclusive 0 to infinity. So now let's look at the domain and range for my logarithm. Remember, the inputs of one become the outputs of the other, which implies that the domain of one becomes the range of the other and vice versa. So I recognize here that for my logarithm function, my domain, notice it now has a vertical asymptote. It has a vertical asymptote at x equals 0, which means my domain is now non-inclusive 0 to infinity. And my range, f of x, is now negative infinity to infinity. So you see that? That's really important. So your exponential function has a horizontal asymptote at y equals 0. This means that my logarithm function will now have a vertical asymptote at x equals 0. Okay? So far, I've been able to show you the relationship between the exponential function and the logarithmic function, okay? And notice I'm going to go ahead and go into like translations and all that good stuff because now I'm able to showcase my parent function. So my parent function is f of x, and we're going to just use log base 2 just because it's easy. The most common base that you use in logarithms is base 10 because that's the one your calculator reads. Not to worry, I will show you change your base formula, which will save your life. But let's go ahead and look at how this also applies to transformations. So I'm going to go ahead and just graph again my logarithm function. Remember, it does have a 4, 5, 6, 7, 8. Bum, bum, bum. It does have a vertical asymptote at x equals 0. 1, 2, 3, 4, negative 4. 1, 2, 3, 4, negative 8. Okay. So, and my new anchor point for this one is not 0, 1, but 1, 0, right? So my function, so remember, I'll just go ahead and give you the table of values again. The way you can build this is if you already know the inputs and outputs for exponential function 2 to the x, all you have to do is invert the, for example, right? 0 corresponds to 1. Notice that I went 0 corresponds to 1, output to input, because I'm thinking in my head the exponential function. 1 corresponds to 2, 2 corresponds to 4, 3 corresponds to 8, negative 1 corresponds to 1/2, negative 2 corresponds to 1/4. So that's easy for me to do. 2 corresponds to 1, 4 corresponds to 2, 8 corresponds to 3. Oops, sorry. 4 corresponds to 2, 8 corresponds to 3, and I have something that looks like that. This right here is my logarithmic function, okay? Awesome. So if I want to say, I want to do, g of x is equal to log 2x plus 5. Oh, what? Don't you know it? All I'm doing is a vertical translation 5 units up. Vertical translation 5 units up. So that means if I want to graph that one, g of x, all I have to do is take my anchor point, which is now 1, 0, and move it up 5. So, bloop, right there. And now my function is going to go like this, right there. So this is now g of x, easy breezy. Because my way of reading my transformations on my equations are still very similar. Not to worry. What if I wanted, say I wanted h of x is equal to log 2 of x plus 3. So let's see what this gives me. I noticed that it's in the input, so I'm hoping that we can see that this right here, again, remember, horizontal translation is always opposite of what the equation tells us. Equation is telling us plus 3, but really it means opposite. So this is horizontal translations 3 units to the left. Okay, and let's see what that gives us. So I'm going to go ahead and use my calculator. And I'm going to go ahead and graph. Hope I can put it on here because I also want to teach you how to do this. Oh, nice. So notice I went onto my graphing calculator. Okay, I'm going to hit my y equals right here. And so I'm on the first one. And all I'm going to do is I'm going to go ahead, for the sake of this one, I'm just going to leave it as log. And I'm going to put x plus 3. So, and then I'm going to close it and I'm going to graph. Okay, and I'm going to go ahead and make sure my window is good. Let me go ahead and make it a little smaller. Okay, so and I'm just gonna plug it. So there we go. Okay, so if you can see, my function, I don't know how to put this a little closer, but it's gonna be 2 to the left. So let's go ahead and make a table of values. X, h of x, okay? And I know that I'm probably gonna be 3 units to the left, so I'm gonna look at this one. Remember, I'm always against my parent function, which is f of x equals log 2x. This one's already transformed, this one's already transformed. So I'm gonna pick -2, okay? So -2 is my input. Let's see what we get, okay? So I have, and let me go ahead, I'm going to erase this one just so that we have room and I don't confuse you. H of x equals log 2 of x plus 3. I want to know what h of -2 is going to be, which means I have log 2 of -2 plus 3. H of -2 gives me log 2 of 1, okay? Remember that h of -2 is not a particular value, it's just a label. So 2 to what power gives me 1? That means that h of -2 must be equal to 0 because 2 to the 0 gives me 1. See that? Yeah, so bam, 2 to the 0. Okay, let's go ahead and look at -1. -1. So again, I'm going to be looking at all of this again. So I'm looking for h of -1. H of -1 equals log 2 of -1 plus 3. H of -1 equals log 2 of 2. And again, I use my exponential expertise to show me 2 to what power gives me 2. So this is just the label, but I'm still looking for that value. What is that? So 2 to what power gives me 2? That's going to be x equals 1. So, right? So this right here, h of -1 is equal to 1. Bam. Okay? Okay, let's see what we get so far. I have -2, 0 right there. I got -1, 1. Boom. And I'm pretty sure that at 2 or at 1 actually, let's see. At 1, let's see what we get. H of 1 is equal to log 2 of 1 plus 3. Again, that's my x value. That's why I'm plugging it in here like that. H of 1 is equal to log 2 of 4. 2 to what power gives me 4? This means that this must be to 2. Okay, let's see. 1, 2. I recognize that my function is now like this, which means that this got translated 3 units to the left. Okay? So, where is my chart? Cool. I've given you a little overview of how do we write logs and another little crash course on simplifying exponential and solving exponential equations. So I'm going to post a little exercise on my website. I hope you enjoyed. Stay safe, everybody. Until next time.